Sigmoid method, one of the types of gradient descent. No, sir. Gradient descent is a method to find out the minimum. Maybe the function could have a global minimum or it could have a local minimum. So gradient descent is a method to find out the minimum. It could be global or local of a function. And what is sigmoid? Sigmoid is used as an activation unit. So in a node. So for an example, I have to find out non-linear boundaries, right? So I need to have non-linear transformation of an input. So when I multiply w1 into w into x, this is a linear combination of weight vector and x vector. But when I transform this transformation through a sigmoid function, that it will be transformed non-linearly. So this non-sigmoid function is used in these activation units, in the nodes, right? Every time you get an input from here, this input is, let's say, x, it will this unit will convert into 1 upon 1 to the power e to the power minus x. So this x will convert into this thing. So sigmoid is used as in this. Why I'm using a sigmoid in context of gradient descent? Because to find out the gradient of a function, that function must be differentiable. If you remember or recall your calculus, so if you use a sigmoid function, then your function will be continuous only. How much nonlinear doesn't matter, but it is continuous. But if it is discontinuous, if it is not continuous, then you cannot find out the differentiation of it, right? To make the function continuous, we are using a sigmoid function. If you in perceptron, for example, when we are using step function, in that case it is not a continuous function. We cannot find out the differentiation. So to make the function continuous, we are using the sigmoid units activation function. Is Can we use any other function instead of sigmoid function? Yes, sir, we can use tanh, relu. There are a lot of functions are there. So one is step function. I told you in step. So two functions I already told you in this lecture. One is step function. Other is sigmoid function. Other is tanh function, right? So there are a lot of functions that you can use. Generally, whenever you read neural networks, you will find that sigmoid, it is given by taking sigmoid example. How can we decide when to use regression neural network for learning in classification? Hmm. So neural networks are used when the true function is not known or very non-linear in case, very non-linear. So for an example, in speech processing, it is found out that if you have to classify, let's say, 10 vowels. So this is vowel 1, vowel 2, vowel 3, vowel 4, vowel 5, vowel 6, vowel 7. If I plot into two dimensions, so this could be a decision surface of this. If you want to classify this kind of if you want to find this kind of a decision boundary, you if you use neural network, you can easily get this. So when your decision surface is quite unknown and it is very complex in non-linear in nature, then you use neural networks. If you little aware about the happenings around you, then you a lot of hearing about deep learning. What is this deep learning? Deep learning is nothing but just a big mess of neural network which can able to predict the problems, which can able to solve the problems in very efficiently in respect to the problems when we did it with the other methods, right? So okay, so let's start with this numerical. mm. So here is my neural network. Why the idea behind it? can we get a perceptron weight using least square? You mean to say, can we learn the weights, right? Yeah, we can learn this. So this is what we have. This is the neural network that what I am going to use for explaining what I have discussed so far in my previous hour. And the motive of this neural network is that every time I give my input, so here input is two-dimensional, so I am representing my input I as two-dimension vector, that is I1 and I2. So this is having two components in it, I1 and I2. And the motive, I want to train the neural network in the sense every time I give the input, I will get the same output. So for an example, here I am giving 0.5 and 0.10. So this is the input I am giving. My motive is to design that every time I give the whatever the input I give, I can get the same output. So I get the same output. So this is my motive of this neural network. Randomly I have taken randomly I have taken some weights. So this is my first weight, W1, W2. So this is W1, this is W2, this is W3, this is W4. Random weights are taken for these weights. Likewise W5, W6, W7, W8. So there are 8 different weights. The bias of this node is B1. Here for the simplification we have taken bias constant for both nodes, B1 equals to 0.35, that applied to both nodes. Or you can see like this, this is a bias node B1 and it is connected like this. So you can visualize like this also, but for simplification, not to make the figure messy, I have write this the bias here directly as B2 equals to 0.6, 0.6. So these two bias are applied, these two different bias are applied to these four nodes B1, 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 B2, B2, right? And sigmoid function is used here for non-linear transformation of input. So what do you mean? What I mean by every time I give the input to the function here x, I will get output equals to 1 upon 1 to the power e to the power minus x. Whatever it goes to the inside of this node, it gets converted by this sigmoid function, and I will get this output. The other thing is I am denoting the input of a node by net input, and the layer, for an example, I am talking about this layer, right? So I am saying that the input that I am getting to this node here is net h2. If I am saying the input that I am getting here, that is net h1. Similarly, the net input I am getting from here, that is net o1. Similarly, net o2. So that's how we are saying that for every node I have some input that I am denoting by net, and the output after transformation. Transformation means after getting a sigmoid function applicable on that input. For example, here when I get input x, so here my net is x, and when the output will be this sigmoid function, so this will be my out. So net will be x here and out will be 1 upon 1 to the power e to the power minus x. So whatever the transformation happens in between due to the sigmoid function, that is denoted by out. So I hope that the notations are quite clear. T is a target, right? I will be used, no, so whatever we have used, this is T0 is the output by by this neural network, and this T1 is the another component output produced by neural network, right? So these T1 and T2 are the outputs that are produced by neural network. I1 are the input that is given to the neural network. W1, W2 are the different weights, 8 weights, and there are two biases, B1 and B2. And for node, I told you that the net input is called the whatever is going inside, it is denoted by net input, and whatever transformed by the sigmoid function is denoted by out of that node. Fine. Okay, great. Any nonlinear function output can be calculated using this. Any nonlinear functions output can be used. Oh my God, what this question is. So there is one question, and that is quite. Uh, what should I say? It is saying that any nonlinear functions output can be calculated using the sigmoid function. I don't understand this question, but I will tell you again what I am saying. If you want you are using some nonlinear function, there are lot of nonlinear functions are there. One is sigmoid among them, other is tan h. These are nonlinear function. One is ReLU. So there are a lot of non-linear functions are there. When you want your non-linear transformation of some input, so for an example, this is a linear input x. You want to you want to do non-linear transformation on it. You pass this input to a sigmoid function. What a sigmoid function will do? It will do this. Whatever the output of this expression will be, let's say this expression will be now xl, and this will be this is x and l. So this was linear in nature, x was linear in nature, but when it goes through this node it will put pass through a sigmoid function. This is a sigmoid function here. So the output now you're getting is non-linear in nature. So this is what I don't understand this question. Any non-linear function output can be calculated. So I hope that it is clear now. Is there any difference between O and T in this context? No, sir. O and T are exactly the same, but I don't want you to confuse with the notation. For here in this graph, you just forget what is O, right? So here I'm using in this network here I'm using for the nodes here, O1, O2. O1 is the first node of output layer, and O2 is the second. O2 is the second node of the output layer. So please forget everything before what we have used here. O1 and O2 are the notation for the nodes, right? And T is the output. T0 is the output by a perceptron, and T1 is the output of the second perceptron. Second node, right? So fix to this notation for a while. So forward pass. What is forward pass? Now let's calculate what is forward here. So this is first time. What I'm doing here is this is question. So have we fixed the output and then calculated the weight with backward calculation? So please hold your questions for a while. So until I will cover up this numerical. So what I'm doing here, this is my forward pass. What I'm doing in my forward pass, this is my input, right? I1, I2. And what this I1 is doing, it is multiplying with this W1. So I am multiplying this I1 with W1, and this so this is also this this is, oh my God, what I have done. This is I0, I think. No, this is I1 and this is I2. Sorry for the mistake. So this is I1 and 2. So this I1 also go to this path. This I1 also go to this path. So these both are I1, right? So I1 multiply by W1, right? And this I2 will go to this path also, right? So this I2 multiply by W2. So the net input to this node H1. So the net input to this node H1 will be net input to the node H1 will be W1 I1, this W1 I1 plus W2 I2, this W2 I2, this is W1 I1, this is W2 I2 plus bias, and I have taken I0 here. I0 is nothing but the value of I0 is 1. So plus bias. So net H1 equals to W2 I2 plus W1 I1 plus bias. And when we calculate it, So this is my bias is 0.35, right? This is 0.35. Bias is 0.35. I0 is 1. W1 is W1 is 0.15. So this is 0.15. This is my I1 0.05. This is W2. This W2 is 0.20. So this is W2 and this is my I2, that is 0.10. So when I put it into this thing, so the out input to my H1, the input to my net input to my H1 will be this 0.3775. Similarly, the input to H2, what is the input to H2? This is I1 coming here, right? This I1 get multiplied by W3. So this I1 will get multiplied by W3. And here I2 is coming. It will get multiplied by W4. So I1 multiplied by W3, I1 multiplied by W3, I2 multiplied by W4, and I am adding bias to it. So when I'm calculating, I'm getting something this 0.3925. So the net input here I am getting net H1, right? This is net H1. Here I am getting net H2. These are the two inputs that I am getting on these nodes. When I am getting these inputs, now I have to transform this input through a sigmoid function. So this input, right? This is the input. This I feed this input into a sigmoid function, and when I transform this input is through a sigmoid function, I get some output. So this output is out H1. I told you, right? This is the out part, out H1. And when I take this net input to this is net H2, right? When I feed into this sigmoid function, I get this output. This output will be out H2. So this is out H2. Okay. So this is simply what we have done. We have taken input multiplying with weight vectors, find out net input to a node, and when I found out what is the net input to a node, I am transforming it through a sigmoid function. I am getting some output. That's it. So let me clear this. Any question on this so far? I hope this is crystal clear to everybody who is listening this. Right? Okay, let's go further. So so I am here, right? I am here. Oh my God. I have calculated what? I have calculated out of H2, out of H1, right? Now let's go further. I will take this as input now, as I have taken I1 here, I2 here, right? Similarly, I will take this as input, and I will take this input goes here, out H1 multiply by W5, out H1 multiply by W7, out this out H1 also goes here, it multiply by W7, out H2 multiply by W8, and out H2 multiply by W6. So similarly into the next phase, this is my out, right? Out H1 multiply by, so please come to this box here for a while. So this is out H1 multiply by W5. So this is out H1 multiply by W5, and I'm calculating the net input of this node, right? So this is one input which is out H1 multiply by W5, and this is the other input which I have to sum up. This is W6 multiply by out H2. So this is W6 multiply by out H2, right? So now I am taking a sum of these two and adding a bias to it. So this is B2. So this is B2 bias, and just for the sake of conventionality, I have taken out H0, which is nothing, equals to 1. Out H0 equals to 1. So it is nothing but simply I am adding bias to it. So this is first input I am getting, second input I am getting, I am adding bias to it, and this is my net input to O1. Similarly, what I will do, I will take this is O out H1 multiply by W7, O out 1 multiply by W7. Let's switch the color for a while. So this is out H1 multiplied by W7, out H1 multiplied by W7, and like out H2 multiplied by W8, out H2 multiplied by W8. This is out H2, right? And I am adding bias to it. I am adding bias to it. This out H0 equals to 1, so it will not play any role. Finally, I get net output. So this is I am getting here. This I am getting net output 2, and similarly I am getting net output 1, right? So this is again the same process I have taken. Now once I calculated the net output, I have to find out what is the output of this node. What is the output of this node? So to find out the output of this node, uh, I have to transform this net input through a sigmoid function. So this is my net output 1, this is my net output 1, and I am taking this net output 1 and transforming it through a sigmoid function, right? When I transform it through a sigmoid function, I get some output. This output is what I will get here. This is 0.7513, 7513. This is the same thing, 136507, right? So similarly, I will take the net output and transform it through a sigmoid function. I get the second output, and this second output I will get here. So this is 0.77 something, right? 7729. So these are the two outputs that I will get from here. I hope this is also clear. Now this is how I will be calculating the total error. The total error is nothing, the target minus output. So this is my target 0.11 and 0.99 here, and the output what I am getting from that thing. I am just subtracting it from this square, subtracting it and taking the half of it. Finally, I am adding these two expressions, and after adding these two expressions, I am getting this one. So this is the total error that I am getting. The total error is getting the come again here. So this is first component I am getting E01. This is important to remember. And this is E01 higher calculated. I calculate whatever I am getting from here, and what is this here written here. So this is the difference of this. Similarly, what I am getting here and what is written here is that it is the difference of this. I am taking a square of these both terms and dividing it by half of it, and then this is what I am denoting by E01, and this is what I am denoting by E02. I am adding it, so this is my total error. So this is what I am getting my total error, E01, E02. If another function is used instead of sigmoid function, will the error will be different? Yes, madam. So obviously there is one question that if we use some different nonlinear function instead of sigmoid function, obviously that error will change, or error will get changed, because the output through the non-linearity transformation will be different, right? And that's why my input will get changed. So this is what we have. There is one question for target. We are doing 2 iteration of linear calculation, bias Wi plus sigmoid. Why it is? Because is it because given? What? I don't understand this question. For target, we are doing 2 iterations of linear calculation. You mean by 2 iteration means 2 layers, right? First hidden layer and the second is output layer. So it depends upon how many layers you are taking. It is a design issue. So for now, to understand what is neural network, I have taken 2 layers. One is hidden layer and other is output layer. The hidden layer is denoted by H1, and the first layer, that O1 and O2, is the output layer. There is one question, how to determine which is the best function. What do you mean by best function here? I don't know what is the best. Okay, you mean to say activation function, right? So active means to say which whether a sigmoid or so for time being just focus on sigmoid, right? These are very deep issues that you are talking about. Deep issues means to say there are a lot of literature available. I cannot explain in a sentence. So far we have calculated what is our output, right? My God. How do we calculate values W1, W2, W3, and W4? So here we have assumed that the network we have taken is a random values, that W1, W2, W3, W4, whatever you have seen in this example are the random values. So we will see how to update these values. Why, the second question, why did we use two sigmoid functions to process the output? We didn't use two sigmoid functions. So there is there is one hidden layer, right? There is another hidden layer. There is third hidden layer. There is fourth hidden layer. There is fifth hidden layer. The number of hidden layers you will have, the number of activation units you will get. For an example, this is have three units, three nodes. This is having four nodes. This is having two nodes. This is having three nodes again. So the number of nodes will be having a sigmoid in it. Every node have a sigmoid in it. Every node have a sigmoid in it, right? So it depends upon how many layers you take. The number of layers you will take, the number of non-linear transformation will happen. So then the deep it will be. For an example, the more deeper this network will be, the more your hypothesis space will get converted into, like it will able to transform it will able to design a very complex boundary. For an example, this kind of a boundary. For an example, one node only able to take a line in a space, in two-dimensional space. For an example, if you want this kind of a decision boundary, here these two nodes are there, and other these plus nodes are there. So for this for this kind of decision boundary, you need two network, two layers. For an example, if you need this kind of a decision boundary, then you may take five networks, five layers in that. So it depends upon how much complex your decision surface or boundaries. The number of decision layers will be decided on that. So do we desire e total to be ideally zero, or does that influence our choice of function? So the desire of e total is always zero, right? So last question, I don't want to miss this quick my class. So last question, how do we find how many layers one has to take of a learning, how it's calculated? So just for you, I want to suggest that people are writing papers on it, and what they generally do, that they come up with their own creative design. Like for someone, but one person is using three layers in his network, and he's saying that I got 50% result on my network, and other person is taking five layers in the network in different way, and he's saying I'm getting 80% of the result, and he's publishing a paper on it. So likewise, this is a design issue. So for an example, deep neural networks, if you go and read these deep neural networks, Google come up with some different design and different number of layers, and each layers how many nodes should be there. And let's say Amazon will come up with different network, and he is taking different layers, and in each layers may have different number of nodes. So this is a design issue. We cannot, it is not hardcore. There is no hardcore rule that you have to take these number of layers, and each number of layers should have these number of nodes, right? So let's hold your question for a while, and I want to finish the backward algorithm, because this is more uh, tougher than what we have learned so far. That was a forward pass. So please be focused on it. Now my intention is, I got a total error, right? So I got a total error. If you remember my previous slides, what I was doing, I have an error function. I am differentiating that error function with my weights, Wi. So here I have eight weights. So W1, Likewise, I have to differentiate it with W2 and up to W8. Every time I differentiate it with the weight, what for example I am differentiating it with W1, so I am getting some direction, differential direction. I am multiplying it with learning rate and adding with my previous weight what it is. So this is how I am updating my W1. Similarly, this is my differentiation with the error function with W2. So this is what my gradient is giving me the direction when I am changing my how much W I am changing and what is the effect on the error with changing in W. So this is what I am calculating by the gradient or differentiation with partial differentiation of this error function. So this is what is the change that I am getting when I change little W2, the error, that how much it is changing. I am multiplying it with learning rate and adding it with my previous W2. So this is how I am updating my W2. Likewise, I am updating all my weights like this. So I need to know what is my differentiation with particular weight. So hold your questions for a while and please go with me through this network. So here I am differentiating my total error, right? Total error was E0, E01 plus E02. And E01, if I want to write, that is half of target 01 plus out 1 square. And similarly, E2 will be half of target target O2 minus out O2 square. So this is the sum of these. The total is the sum of these two functions, these two expressions, first expression and second expression, right? So I am differentiating my total error. I am differentiating my total error with W5 weight, right? So ignore this B2 for a while. I'm not changing B2 in this case to, but it can also be changed. But to understand, to make it understand, I am only differentiating my error function with the weights only, W1, W2, W3 up to W8. So this is my W5 that is coming. If I will show you, if I show you that network, right? So this is W5. I want to find out what should I change if the what is the impact of change in W on the total error. How will I find out the impact of W5 on the particular error? I will differentiate. I will find out the change in W5 is the change in the error. That is what is given by differentiation. So how will I get it? This is a chain rule. If you recall that differentiation rule, I am differentiating total error with W5. So total error, how can I write my total error is, this is my total error. I will total error is the resultant of output 1, right? Because I want to find out what is the differentiation, what I want to differentiate it with W5. So total error is, there are two nodes. This is E02 plus E01. So this is the sum of this. But I want to differentiate it with W5. I can see from here that W5 doesn't have any impact on E02. W5 don't have any impact on E02, so I will discard this. This term as this term will be treated as constant because W5 doesn't appear in this expression, right? So the only one term left, that is E0 out, E01. What is E01? E01 is a function of out 01. So I need to differentiate E total with out 01. Then out 01 is the resultant of net 01. If you remember, we transform it through a sigmoid function, right? So I want to differentiate this out 01 with net 01 because out 01, the change in out 01 will be a resulting change in net 01. Finally, net 01 is the resultant is somewhere affecting by W5. So this is a chain rule. So this is a chain rule. So I want to repeat it again. E total is somewhere here. This is this term plus this term. This term is constant, we are ignoring it. Finally I left with E. This term is, it is a total error is a resultant of this variable. There is a variable, so I am differentiating it with this variable. This variable is a resultant of this variable, so I am differentiating it here. Net output, and net output is a resultant of these sums, right, if you remember. So that's why I'm differentiating net output with W5. So if I want to find out my differentiation of total error with respect to W5, I need to calculate these three terms individually, and I can multiply these terms and then find out what is that. Let's see it. Oh my God. So this is the E total with W5. This is E. I'm differentiating it with W. So I used here this color convention. So the green color represents the green calculation, blue represents the blue calculation, and this uh, yellow represents the yellow calculation. So I am calculating here E total upon E out. So if you remember, this was my total. This was my E01, and this was my E02, and this was a sum of this total error. So this is E01. This is E01. This is E01 total output. I am talking about total output. Total output is nothing but the sum of this total E01, and this is E02. When I am differentiating it with output O01, you can say this here output 01 is not appeared in this function at all. So it is termed as a constant, it goes to 0. Now I left with this only this expression. When I differentiate out with this character function, this is a square of it. So x square, the differentiation of x square is 2x, right? So it will finally convert it, what it will, this 2 square, this 2 will get cancelled with this 2. And I left with this function target minus out of 1. When I differentiate chain rule differentiation of this without 1, I will get minus 1. So this one minus 1 was minus is here, and this term gets here. So this is, if you don't recall what is differentiation, so for what I am doing nothing great here, I am just differentiating it. I am just differentiating A total with out 1. When I do it, I got this expression. I know what is my target. My target was 0.001, right? And this is my output of the node. This was the output of the node when I had something in net O0. This is my output O1, output layer first node. This is my net, and I am changing it through a sigmoid function. I am getting some out at O1, right? So this out O1 will be, this is here. So I am using this minus what is my target. I am just subtracting it, and I'm getting this expression. Similarly, when I want to calculate what is this expression net out. So what was net out? Net out was nothing, but it is just a node I am getting. This is net here I'm getting, and it is out I'm getting out here. So I'm just differentiating this out with respect to this net, and how it is related. This net is nothing 1 upon 1 to the e to the power minus net, right? This is how I am using it. And you remember the differentiation of this rule was, I told you tau x 1 minus tau x just few slides before. So it is nothing out 1 minus out 1. I am using the value of out 1 which I already calculated here, right? So this is out 1. So this is out 1 we have calculated here, right? So out 1 minus out 1, when I calculate it, I got this value. Finally, this is my net input. This was my node. This was my out here. This was my net here. Net is nothing but the sum of the product of weights with this input, the product of weight with this input, whatever I'm getting here. So this is net O1. So what is the net input of O1 node? So it was It was bias W5 multiplied by O out H1. So here H1 node was there, right? So the output what I was getting from here, I was multiplying it with W5. So out H1 multiplied by W5, out H2, whatever I am getting here, this was multiplied by out H2, right? It went to here as net 2, and it was multiplied by W6. So this was out H2 multiplied by W6, and this is W5 multiplied by out H1. So this is my net O1. So this was my net O1 when I'm differentiating with W5. This is a constant term. This is a constant term. Only this is having W5. So I will get out H1. Out H1 is nothing. We already calculated it. What is out H1? Oh my God. This is what we get out H1 here, and this out H1 was this. We calculated it in the previous path. Finally, we have calculated all three expressions here. This green, blue, and yellow. So this is calculate. Finally, I am multiplying all these three expressions here, and I am getting the total error that I am getting by change in W5. So this is E total. I have already calculated in my previous slide, right? Uh, so this is E total I have calculated here in this green. This is blue I am calculated here, and this is yellow I have calculated here. And the total error when I differentiate it with W5, it is a multiplication term. So this is what I got from here. Now this is a differentiation. If I recall the rule, that was the learning rate multiplied by the differentiation, right? And what was the previous value of W5? So W5 previous value was 0.5. So oh my God, this is 0.40. So W5 value is 0.40, right? So this was a previous value. So this is 0.40, right? It doesn't make any difference, 0.4 or 0.40. So this is the previous value of W5 learning rate multiplied by what I am getting by the using of differentiation. This is the same value. When I'm multiplying this and multiplying with the learning rate, I'm adding it to the previous rate. I'm updating my W5 this. So my new W5 will be this. Similarly, my W6 will be changed, W7 will be changed, W8 will be changed. These are the new values. So in my first layer, I showed you how to change, how to update W5. Whatever the random value you decide for W5, it will get updated according to the error what you are getting, right? Now last step. So sometimes you see these expressions, sometimes you see delta output 1. Delta output 1 is nothing but the total error with the output differentiation and output differentiation upon the net differentiation. Sometimes the people denote it with the differentiation of this. For now it is not important to understand this. Okay. Okay, this is hidden layer and it is important. I want you to please focus on this, because if you understand this part, you will understand this whole neural network. From W6, W7, W8 also we need to run through same amount of calculation as that of W5. Yes, sir. So there is a question that how W6, W7 and updated. So similarly, I just don't want to make a mess on this slides. I just used only one updation. So because all the other updations are very similar, like W6, W7, W8, so all are similar, so you can do it. Why to update W5? I will take these questions later. But do you understand these things? W5 is updated because I am getting some error, right? I don't want any error. I need to change weights to adjust so that my error can drop down. That's why I'm taking the gradient. Gradient is finding out that point where I am getting that minimum error. because of the weight. So I'm just finding out what are my new weights that can help me to reduce the error, and that's why I'm taking the gradient of all these error function. You forget those that figure where that bowl was there of that gradient descent, right? When you guys say okay, then that was a really relief for me. Okay, so finally this is a hidden layer here, and it is important to understand. So this is, I want to find out, this is my total error, right? This is the sum of E01 plus E02. This is the total error, and I want to find out how much the change in W will affect this my total error. This is my first task, to find out the differentiation of the total error with respect to W1. Here you can see that if you change W1, this will get changed, output will get changed. Because of the output, this will get changed and this will get changed. When you do back propagation, so similarly you need to find out what is the gradient that is coming from this root, what is the gradient coming from this root, and finally you add this thing and find out what is the gradient you are coming from this root, and finally W2. So don't want to make this more messy and complex. So you just understand how what are the steps, and later you will see the figure and try to try to form the intuition of it. So what I am doing here, this is my, again, E total into W1 is the product of three terms. I'm differentiating my total error with respect of out H1. With respect of out H1, this is out H1, right? I am differentiating my total error with out H1, and then out H1 with net H1. This is my net H1, right? I am differentiating my out H1 with net H1, and this net H1 is differentiating by W1. So this is straightforward. We have done into the previous calculation it. This is out is differentiated by net, and net is differentiated by W1. So this is, and this is important here. E total is this. You are differentiating it with, out H1. So this is out H1 here, right? You are differentiating this total error with this term. So this term is total error is a sum of EO1 plus EO2. So you are differentiating these two individual terms that are by OH1 separate and OH1 separate, and then adding, then you find the total gradient of it. Okay, so this is total. So I'm calculating first. I'm just first calculating this expression here. I'm calculating this expression first. This is important. So EOH1, this is H1, out H1. I am differentiating it first EO1. So how out H1 is differentiating by EO1. The EO1 is out O1. So EO1 is out O1. I'm differentiating this function with out O1, then out O1 with net O1, and then net O1 with out H1. So this is H1. So this EO1 with out O1, this is out O1, and this is O1. I am differentiating with this. Then out O1 with net O1 because of this function. Then net O1 with out H1 because of this branch. So this is again the product by chain rule of differentiation. So first I am calculating my first term, EO1 by out H1. You remember EO1 by out H1? So this is my EO1, right? This is EO1, node of the difference of target and output by O1. This is constant, just remove it. It is same what I have calculated here. So this expression I already have it. So, oh my god. So similarly I calculated net out O1. We have already calculated, right? This is out O1 by net O1. We have calculated it in the previous lecture, previous slide. And this is net O1 W out H1. Let's see what is net O1. Net O1 is B2 out OH, W5 out OH, and this is we already seen it. Now when we calculate differentiate with the out H1, this goes out constant, this goes out constant, this this will left W5. This is chain rule, and this is 0.5. When you multiply, you will get DEO1 without H1. This is this. Similarly, when you calculate EO2, you get this. You have to add these two terms, and you get this. So this is you calculated DE total without H1. This is you calculated this term only. Now you have to calculate it this term, and now you have to calculate this term. Then you have to multiply it. So you have calculated this term. Now you are calculating this term. This is quite easy because I am here now. This is now out H1 hidden layer, right? And this is net H1. Out H1 net H1. This is out H1 minus similar expression. You get this one net H1. Oh my God, net H1 into W1. Net H1 is B1 I0 W1 I1. When you differentiate it by W1, you get with only I1. This is I1. When you multiply here, this is I1 value, right? 0.05. You get this expression. So you get finally when you multiply it, you get the differentiation of total error with W1. Now you are taking the sum learning rate differentiable value that is here, multiply adding it with W5. Oh sorry, this is not W5, this is W1. You are adding it with the previous value of W1 and you are getting this value. Similarly like W5 W2. So here you see that when you had previous iteration, this was the error, but after the updation, this is the new error which got dropped down. So my first when I used my first weight, my error was this. When I misused my second weight, my error is this. So my error goes down. So with this lecture is finished, and please go through it, right? Thanks for this. Okay. See you then tomorrow.